Good evening, everyone. Myself Gautam Sharma. I welcome you all in a Sapience Education. So today I am going to discuss about the moving charges and magnetism. This is a part 7 video. So the topic which I am going to discuss is the torque on a current carrying coil in a magnetic field. So let us suppose this is a coil. Okay. So from figure you can understand that this is a coil. Okay. So this coil, it contains a current, right? So its coil is fixed in such a way that if current passes and there is a magnet this side as well as this side. Red color is your north side and this is your south side. So what will happen if you put a current on the this conductor or in the coil? So this is made up of a copper, right? Copper. So when you pass a current on this copper, so what will happen? It will automatically start rotating. So why this happens? So we will study the basic principle first of all. Okay, on the basis of that principle only we have done lots of experiment. So let us check it. Now see here, torque on a current carrying coil in a magnetic field. So basically you know that torque means what? Torque means what? Turning moment. Okay, so let us consider this is any object and it is fixed in one end. Okay, when you start applying a force, so what will happen? It will try to rotate. So rotation happens due to torque only. Okay, so similarly there is a current carrying coil and it has been fixed in such a way that it will only rotate. It will not move forward, not move backward. It will only able to rotate because it has been fixed in a, a rod like this structure. So let us know the basic principle of this. When a rectangular current carrying coil is placed in a uniform magnetic field, then it experiences a torque. It does not experience net force. What do you mean by this? Try to understand here. So let us suppose this is your current carrying coil, right? Current carrying coil. So this is, let us suppose, current carrying coil. Okay, and it has been kept in around a magnetic uniform magnetic field. So let us suppose this is a magnet. This is a magnet. This is a magnet. It is your north pole and this is your south pole, right? This is a south pole. Got it? This is a south pole. Now what happens? There is a magnetic field line which will pass through this. So what will happen? There will be an induction of a force. So whatever we have studied, any current carrying wire will experiences a force when it is kept in a uniform magnetic field. So here what happens? A current carrying wire experiences a force. Why? Because it is put in a uniform magnetic field. But we have kept this coil in such a way that it will not move up and down. It will try to rotate. Where it will rotate? See here, the force will act upward, some force will act downward. So net force, let us suppose upward force is 10 Newton. So downward force will be also 10 Newton. So total net force is 0. Net force is 0. But what will happen if net force is 0 but both the forces is acting along opposite direction and there is a hinge? So what will happen? It will try to rotate. Okay, so as you have already seen in the diagram, see here, this is what it is happening. It means that it has been fixed. See here, it has been, there is a fixed and it is rotating, right? So let us go ahead. So consider a simple case when the rectangular loop is placed such that the uniform magnetic field in a uniform magnetic field B is in the plane of the loop, right? So this is your A, this is omega, right? This is the magnetic field B. Now what will happen? Try to understand. This is the rotational axis, right? This is the rotational axis. So what will happen? The field experts know force on the two arms AD and BC. Why? See, there is how many arms? See here, there is how many arms? Let us consider this is A, B, C, and D. So in these arms, no force is being acting. Why no force is being acting? Because any current carrying conductor is parallel to the magnetic field, so force will become 0. So what we have studied, any current carrying conductor will placed in the uniform magnetic field and it is parallel to the magnetic field. So what will happen? Force will be zero. So basically what we have learned from here this section, and in this section what happens, the current carrying is parallel to the magnetic field. If you want to see the magnetic field direction, so let us see here. So this is the magnetic field direction, this is the magnetic field direction, this is a magnetic field direction, right? So this is the magnetic field direction, and the current carrying wire is also parallel to the magnetic field. So if current carrying wire contains parallel to the magnetic field, so what will happen? No force will be zero. So hence this side and this side there will be no force. So this is what it is written. So the field experience no force on the two arms AD and BC of the loop. So the magnetic field is perpendicular to the arms AB and the loop, and the external force F1 on it, which is directed into the plane of the loop. So let us consider this is a arm B, right? A arm AB. Okay. So in this arm, so what happens? In this arms, the force is acting, right? So if you use Fleming's left hand rule, so what will happen? As per the Fleming's left hand rule, current, see here, see, as per the Fleming's left hand rule, try to understand. If you have already done these things previous classes, in the Fleming's left hand rule, the magnetic field is in this direction, right? So this is the magnetic field. Current is in this direction, right? So this is the current direction. So what will be the direction of the force? So if you put your finger, left hand, Fleming's left hand finger, so in the magnetic field in the current direction, so you will find a force which is acting downward. So this is the force. So let us suppose the force acting in this side is downward, right? In this side the force acting is downward. So this loop force is acting in this downward, and this is our rotational axis. So in this is the axis is fixed, so only it will able to rotate. Now if force F1 is downward, now let us suppose in this case what happens, the current is coming in this direction and magnetic field is acting in this direction. So what will happen, if current is carrying in this and magnetic field is acting in this direction, so what will happen, the force on the current carrying wire will act top upward. So the force here will act upward. So what you have seen in this whole coil, the one force is acting, sorry, one fix is force is acting downward. See here, one force is acting downward and another force is acting in a upward direction. So what will happen, there is a distance between them. So a torque, automatic torque will be created, torque. So this torque will be created and this torque will try to rotate this in the omega, angular velocity omega, right? So this is what is happening. So try to understand this. So I hope you have understood this. So finally, F1 is the force on which the directed into the plane of the loop. So finally, force will be equal to I into B, which is the length, and the magnetic field. What is B? See, this is the B length. See, this length is the B length, total length of the wire. Okay, and this side the length of the wire is A. So we want this B only. So force is equal to I into B, small b into A. So this B is the length of the wire, length of wire, and we know that force is equal to IBL. Force is equal to, or IBL, not IBIL, BIL. So B is the magnetic field, I is the current, L is the length. So here B, small b is the length of the wire, right? So this is what we are getting a force. Now, similarly, the magnetic field exerts on a force on F2 on the arm CD, which is directed out of the plane of the pip loop. So F2, let us suppose F2 is equal to I2, I into B into B. So same. So this is equal to F1. See here, in this direction also force. So in this length also, this length is also B only. So the force is acting on topward. So force is equal to magnetic field into length into current I. So what you observe, that force on these arms and force on these arms both are same. That is F1 is equal to F2 and this is equal to capital B into length of the arm into current. So this is what we have got the force. So finally we have got the force F1 is equal to F2. Thus, net force on the loop is 0. So let us consider this is F1 and this is F2, and the force acting on this loop is 0. 0. But there is a torque on the loop, and torque on the loop due to the pair of the forces. So what about the torque of the forces? So torque, we know that torque is equal to force into perpendicular distance between them. So the perpendicular distance between them is your a by 2 into a by 2, that is total length is a, right? So the perpendicular distance is a. So finally torque will be equal to force into perpendicular distance, right? So from here, okay, so finally torque, if you want to find a torque, so torque will be equal to force into perpendicular distance. So this is equal to B, capital B, I into B into A. So B into A is the what? See here, if you see this rectangular component, so this rectangular coil, it has a length B and this is A. So B into A will be area of the coil. So you can directly put here, then the torque is equal to B I into A. So this is the area of the coil. A is the area of the coil, isn't it? So I hope you have understood this is the area of the coil. Now consider the case when the plane of the loop is not along the magnetic field and makes an angle with the it. See, it is not always that the it is not it is perpendicular. Okay, so what happens? It may makes an angle, this angle. Okay, so let us consider this is making an angle theta. So let the angle between the field and the normal to the coil be theta. So sine theta is equal to how much? Now see here. So since this is the angle theta, so this will be also angle theta and this is the length. So what will happen? Sine theta is equal to this perpendicular by hypotenuse. So OT by hypotenuse is A by 2. Okay. So finally OT is this length OT is equal to A by 2 sine theta. Okay. Now let us check it. The force on the arms AB and CD is F1, F2 is equal to IBB. So the magnitude of the torque on the loop is equal to F1 A by 2 sine theta plus F2 A by 2 sine theta. Why? Because we will now use sine theta here, right? A by 2 into sine theta. Because force is not F1 now. It has this component. F1 is not now, force is not acting F1. It is F1 into A by 2 sine theta. F2 into A by 2 sine theta. Now, finally, you will find that F1 is equal to F2. Since F1 is equal to F2, so what will happen? F1 is common, A by 2 is common, sin theta is common. So this will be multiplied by 2 to get cancelled. So F1A sin theta. So F1A. So F1 has a value IBV into A into sin theta. Now B, small b and A is equal to area of the loop, that is equal to A into B. So in place of A into B, we can put here A. So IAB sin theta. Now current is a scalar quantity, but area and magnetic field both are vector quantities. So we can take here the angle between area vector and magnetic field vector. So torque is equal to IA cross B. Finally, we have got torque is equal to IA cross B. So the loop for n closely one turns. So if one turn is creating a torque of I a cross b, so n turns will create a torque of n I a cross b. Okay, so this is what we have got the torque. So in this way we have got the torque, right? So NIA, what is NIA? NIA is a magnetic moment of the current carrying loop. So NIA is, if you want to find a magnetic moment, so this is considered as a magnetic moment. Okay. and its SI unit will be area per meter square. So now you have understood that how much torque is being applied. So NIA cross A cross B. So if question is being asked, let us consider this is the current carrying loop. Okay, this is the current carrying loop, and it has an area A. Okay, and the current is I, and magnetic field where it has been put has a strength of B. So if you want to find the torque of the rotation, so how you will find? Torque is equal to, and if the number of turns is n, not only one turns, so NIA B, A cross B. So A cross B will depict the angle between area vector and magnetic field vector. Okay, so finally we have got torque. Now there is another term, it is known as magnetic dipole moment. So what is magnetic dipole moment of a revolving electron? So what you have, magnetic dipole moment or moment of the current loop is NIA. So from here, a Bohr's model, negatively charged particle electrons revolves around the positively charged nucleus. So electron is moving like this. So what happens? The electrons having a charge this performs a uniform circular motion around a stationary heavy nucleus of a positive charge. So now tell me, if electron is moving, so it is creating a current I, yes or no? So current I is equal to charge per unit time. Now in one rotation, how much time it has taken? T. So for one rotation, current is equal to E by T. Okay. So now see here, this constitute a current I as I is equal to E by T, where T is the time period of the revolution. So let R be the orbital radius of the electron and V is the orbital speed. Then time period is equal to 2 pi R by velocity. So from here, I current can be written as EV by 2 pi R. So finally, you can find that current is equal to electron with the velocity by 2 pi R. So if you have a radius, if you have a velocity, you can find easily the current. So this is how we can conclude this. Okay. Now there will be a magnetic moment associated with the circulatory movement. So if you want to find a magnetic moment, so this will be IA. And magnetic moment, what is the formula for the magnetic moment? So magnetic moment is equal to NIA, but here there is no number of loops here. So what we have to write? I into area. So area of the coil is how much? Pi r square. Why? Because it is a circular. What we are dealing here, we are dealing with the circular section. So the area will be equal to pi r square. So if area is equal to pi r square, so we can put here IA. So by r square. So I put, if you put the value of I, so you will get EV by 2. What we have got the I is equal to EV by 2 pi r. If you put the value I is equal to EV by 2 pi r, so you will get the final value like this. Now the direction of the moment is into the paper if it is assumed that electron is moving anti-clockwise. So if electron is moving anti-clockwise like this, so the dipole moment direction is into the paper, dot. And if the direction of the electron movement is clockwise, so that it will be cross. That is, it will coming outside. Okay, so these are the direction of the magnetic moment. Okay, so I hope you have understood this. Okay, this is the relation between angular moment and this mu L is equal to E by 2 me. So this is no none of use. So this is sufficient for you. Okay, so you need to practice these things. I hope you have enjoyed the session. Thank you.